Well, welcome to another exciting microcontrollers class. Uh, I was just mucking about with a little demo here that I was uh, playing around with, and I thought you might like to see it. And this here is a screw that's hooked up to a stepper motor, and I'm using a ULN 2003 Darlington transistor array hooked up to an Arduino with a little Ethernet shield. And when you run the stepper motor, you can get a lot of sort of precision over the motor control and the linear motion that's created. And so here you can see small turns in the stepper motor will give you very precise linear motion. And so what I'll do here is I'll move the camera around so you can kind of see what this thing is driving. And that's a little platen with a laser system on it. And this is used for scanning, high precision scanning. And so the little stepper motor is just like the ones we used, garden variety stepper motor, nothing special. But putting it into this hardware with the very fine screw actually helps to get you a lot of precision. So you can take a cheap stepper motor and make a very high precision device. And this is the web interface so that you can increment the steps under web control. And that's my little demo, such as it is. And thought you might like to see that. It's kind of an interesting thing. This is the live version. What you had just seen was recorded, but in fact, we could turn it on and it would start to work as well. Here. In theory, that should start. Yep, that starts right up because embedded system. So we'll turn that off. No sense running it now because you've already seen it run. So that's the that was my little demo. It takes a little while to set these things up. That's why I like to record them. Any questions about the final project? I guess we had a project due last night. Some people had a little trouble with it. Anybody have any troubles? No troubles? No questions about the final project? Because I had a bunch of questions last night. People were, struggling with it at the last minute, and I thought, oh man, why are they doing this at the last minute? Because we tried to go over it regularly during class, and I think a lot of people missed class. In fact, there's a lot of people missing today, but I guess that's all right. Some people said, oh, well, we didn't know that we needed to do A, B, C, and D or something. And I just said, really? How is that possible? Why wouldn't you know that? And you can see what I did over in here. I added to the case statement A, B, C, and D to get the rows correct. And I thought we had gone over that in class as well. But if people are missing class, they're not going to notice this stuff. That had to be added in. In addition, when I did the refactoring, I got rid of a lot of the extra, say, the redundant definitions. And I don't know if you guys had a chance to try and break up your code a little bit with header files and classes. Did people have any trouble doing that? Making a separate .h file for the DAC? No one's speaking up, so I'm going to call on people. Jacob, how'd you make out with that? Were you able to make a separate?
Yeah, wasn't too bad.
Wasn't too bad. Good. How about you, John?
What's that? Sorry, Professor.
Were you able to create a separate .h file and from your .cpp file?
I decided not to do that. I just left the complexity inside the DTMF file.
Oh, I was hoping that you guys would embrace the object-oriented nature of things, right? Because if you look at DTMF, like what does he do? He makes an instance of a DAC, which makes sense, right? Because that's going to encapsulate the complexity of writing to the DAC, which is really what we were hoping to do. Because if later you said, well, let's not use a DAC, let's use, an R2 network or something, that would work differently, but you wouldn't necessarily want it to impact your code. See, like a, different kind of DAC, maybe R2 DAC or something. And then I think it's important to do these sorts of things, especially if you're going to do a library. Did people have a chance to review my my recent video on how to create a library? John, did you see that?
Yeah.
You did. Okay. Was it relatively well understood? Did you?
Yeah. I've seen that stuff before, like earlier this semester, so I understood what you're talking about though. So
good. Yeah. So what I found out was, and this is sort of a blemish on the last presentation, the keywords.txt is completely ignored by the IDE unless it's in a library. I don't understand why they made that decision. I don't even know if they made a decision. Sometimes I think, what were they thinking? And then I think, are they thinking? Maybe they're not thinking at all. So at some level, one could make a compelling argument that the people who are creating these sorts of things are just not thinking. And, maybe that's what's happening. I don't know. Let's see. What else can we say about this? Oh, so we've got the final project. It's done. Everybody's finished it on time, I trust. No one seems to have had any troubles. Shamrock, did you have any troubles with the final project?
Other than the keywords, which I didn't add because I had submitted right before you had sent out the email.
Oh, sure. Yeah, that didn't matter.
Keywords.
Yeah, keywords didn't matter.
There is no difference between doing it with integers or doing it with bytes, right? Like with regards to the output, I know that there's a difference with the formatting and code, but like it'll sound the exact same, right?
I would guess not. Yeah, I think that what happens with integers, you could probably where were you using the integers for the DeckRight?
In the DAC.h, you have two different parts where it says DeckRight byte and then DeckRight int data.
Yeah, so DeckRight byte. Now that's if you're outputting 8 bits. And DeckRight 16, that's if you're outputting 16 bits. But having said that, it's only a 12-bit DAC, so it's going to take the least significant 12 bits and use those. So when you look at the two different DeckRights, right, here's DeckRight for byte, and now here's DeckRight 16. These are different methods, you see. And so they look different, and they are different, and they take different arguments, and they even have different method names. So they are different. I don't know if you, right? Because why? Because if you're just outputting 8 bits at a time, then all you need is to have the least significant 8 bits be 0, and the most significant, let's say 12 bits, well, let's see, the least significant 4 bits be 0, and the most significant, well, shift 8 bits over 4 bits, and then you'll have a 12-bit word with 0, 0, 0, 0 for the least significant 4 bits. I'll put it that way. So in other words, what you want, let's put it in given 0xFF write to the DAC 0xFF0 because you have a 12-bit DAC. Or ignore the least significant 8 bits and just use the most significant 8 bits, but we're not doing that. So that's a way to go. So what you do is you can use the 16-bit version, but you'll have to shift things over if you have been doing that. Is that what you're doing? Are you using the 16-bit version?
Yeah, I use that. I'm just more so asking, sort of like you could play the same notes on a violin or a cello, but like they'll still sound slightly different because it's like a different thing playing the same note. So like I'm more so asking is like the output sounds slightly off.
Well,
like
it's the dynamic range. It's not going to change the frequencies. Just the dynamic range. So at some level, you know, one could make a compelling argument that, yeah, they sound the same if you can't tell the difference in the signal to noise ratio. Now, having said that, an 8-bit signal to noise ratio will be 48 dB. A 12-bit signal to noise ratio will be something like 72 dB. And so if you can't tell the difference between 48 dB and 72 dB because you've got crummy speakers or something or other, then, you know, then yeah, it makes no difference. You know, put it a different way. If you're listening to it on your car stereo with the window rolled down, you've got all this wind noise. You're not going to hear the difference unless you're Superman or a dog or something with super sensitive hearing. So, you know, it depends on the environment too. If you're listening and there's a lot of background noise, you won't notice the noise in the signal. It won't be perceptual. You won't be able to perceive it. Put it that way. I don't know if that made any sense. Does that make sense, John?
I have a question.
Sure.
Would it be more efficient for the computer if you used a short data type rather than an integer, or no?
Oh yeah, absolutely. Right. In other words, if you use byte, right, instead of int, you're using an 8-bit quantity instead of a 16-bit quantity, and that really impacts the storage, right? So if you're thinking in terms of writing 200 samples, going to a 16-bit quantity will double the amount of storage required than doing like an 8-bit quantity. So
I mean, for maximizing the 12-bit DAC.
Oh, I see. Yeah, I'm not sure if the transfer rates get faster as a result. This thing can already transfer at a SPI clock speed of 20 megahertz maximum. And there's just no way a 16 megahertz Arduino is going to get anywhere close to that. You're still transferring an upper and lower byte, if that's what you're asking. So it doesn't really save anything if the least significant 4 bits are 0. It doesn't save you anything. Because it's I don't know, going to end up moving the same amount of data no matter what. And just look at the output buffer. It's a 16-bit quantity. So if you're going to take the output buffer and break it up into 2 bytes and transfer it twice, right, byte 1, byte 0, it doesn't help you, right? Not in terms of being in 8 bits. We're still doing 16 bits worth of transfer here. Why? Because you can't transfer fractional bytes on SPI. He wants to do a whole byte. It doesn't save you anything to just transfer 4 bits. It wants to do a whole byte at a time. It's character IO in that way. And each character is grouped into 2 bytes. And I guess you might call it record IO. Because look what he has to do. I mean, he has to pull thinking high. He has to do a chip select low. He's got to pull the LDAC low. He's got to wait at a clock cycle. He's got to pull in LDAC high. I mean, there's a lot of overhead going on in transferring using SPI. So that, and he's doing that for both bytes, right? Both bytes have to go through. So you don't save anything. I don't know, maybe you'd save a little bit if you were transferring just 1 byte instead of 2. But I don't think the DAC will tolerate it. The DAC wants 2 bytes. So, you know, if you were using an R2 ladder, maybe that would be okay. Any other questions about the project? I don't know. John, did I answer your question?
Yeah, kind of. My question was more just like, I guess you answered it in saying that like the DAC doesn't care about the extra 4 bits. It really just wants 2 bytes. So I guess that makes more sense to me, because I was wondering whether, since a short is 16 bits, right? Is that right?
And on an Arduino, the int is 16 bits.
Okay. What is a short then?
Is there a short? I spelled primitive wrong. What are the primitive data types? Short is a 2's complement 16-bit quantity. Char is an unsigned 16-bit quantity. An int, oh, he's saying an int is a 32-bit quantity. I don't think that's true for Arduino. Arduino data types?
Yeah, that's what I saw when I looked it up. That's why I was confused.
Yeah, I got confused too just now. So he says that a byte is an 8-bit unsigned number. An int is a 16-bit. Yeah, not like Java, right? Java would give this as a 32-bit, but it isn't in the Arduino land, which is what's confusing, right? Because now it's looking like the int is really a short. And now here's the thing called unsigned int, which I've never used. And then here's a long. I don't know if I ever used unsigned long. Now here's a short. All right, so the short is a 16-bit data type. All right, but didn't I just see that, right? Unsigned int stores a 2-byte value. Now that's a 16-bit data type, and int is also a 16-bit data type, right? So here it is, right? Int is a 2's complement 16-bit data type. So you go over here for short. It says short is a 16-bit data type. Short stores a 16-bit value, yields a range of, look at the range, minus 32,768 to positive 32,767. Then I go over here for the int, and what does he say? Minus 32,767. It's the same. There's no difference. What's the difference?
What is the sentence underneath it that says like the Arduino do is for the integer?
Underneath this?
No, underneath int. It says like
int, and they gave you more bits if you're on a DUE?
Yeah.
The int size varies from board to board. On the DUE, the int stores a 32-bit 4-byte value. This yields a range of, oh, okay. So now it's a 32-bit thing if you're on a DUE, and it's a 16-bit thing if you're on an Uno. Holy mackerel. I can't rely upon the size of an int, because if you recompile my library, it's going to start using 32-bit quantities and shifting is going to break. How's that? You know what? You asked such a good question. That's such a good question. So int is different from short if you're on a DUE. Man, that is bad software engineering. Any way you look at it, there's no consistency for primitive data types as you go from board to board. This is why I abandoned C and went to Java. At least I could know the size of an int. Here, you can't know the size of an int. You say, how big's an int? And the answer is, it depends. That doesn't make sense. Who wants it depends as an answer for the size of an int? And so here we go. Arduino doubles are 64-bit precision. Oh, boy. But on an Uno, a double is 4 bytes. Yow. So how big's a double? And the answer is, it depends. No kidding. You know what? I never realized that. They were not consistent when they went from one Arduino platform to the other. I can understand it. This is a 32-bit M0 ARM Cortex processor. This is not a 16-bit toaster controller. But the idea that the primitive data type names don't give you a guaranteed size just sounds like a bad idea every day of the week. But there you go. That's the way it is here in Arduino land. Well, welcome to embedded microcontrollers. What can I tell you? I don't like it, but I don't have the power to change it. And we can't get the Arduino to run Java. So we're stuck. We're stuck with C and C++. I think, unless you guys can find another way to. Actually, I saw an embedded BASIC, a tiny BASIC for the Arduino. I even downloaded it, but I couldn't get it to work. So I don't know, make that an extra credit project for somebody, I suppose. So, John, does that answer your question?
Yeah, it does.
It's not a good answer, but at least it's an answer.
Yeah. So in theory, if you were to use a short, it could help you, or it might not, right?
Yeah, I think the answer is in the case of a DUE, the short will be 16 bits, the int will be 32 bits. But in the case of an Arduino Uno, there is no difference.
Okay. Yeah.
And that's the way it is, I guess. Sorry about that. It's not my fault. So what other questions do we have? Any questions about the final? We've got a final coming up. Let me review the dates on that. So the final is due on the 17th. I'm happy enough to answer any questions you have about the final, if you have any. Or any questions in general about the course or other courses.
So you said we can't write Java to an Arduino, but how do you select, or how is the language of a microcontroller determined? Like, how do you know which languages are compatible with which microcontrollers?
Actually, it may be possible to get Java to run on an Arduino. What you need is a compiler. So if you were to, there are compilers, ahead of time compilers for Java. I don't know if we can get a Java compiler for the Arduino. I hadn't really looked into it. Actually, you know what you really want is a, well, let's see, Arduino Java compiler. Yeah, maybe there is one. No, IDE is a Java-based IDE. That we know. I would say this. You should be able to find a compiler for every language. But having said that, I mean, if you said to me, well, let's go use the Arduino Basic, and maybe there's a tiny basic that you can get, Arduino Basic Interpreter, right? So somebody did it. I tried it, and here's an example of it running. You can download it, you can play with it. I think it's like a science project gone bad, but I'm not expert at it. And if somebody were to want to try this and get it to work, I think that would be a very fine thing. Maybe it would work good for you. But the reason you don't do this, there's good reasons not to do it. The reason you don't do it is because it just consumes too much resource. And if you're trying to do real-time stuff, like digitizing off the ADD converter and running a DAC, it's not efficient relative to, writing a tight little C program. Because this is probably going to run as an interpreter. This is not even an ahead of time compiler. So I don't know. You got to kind of play around with it. I've actually run Unix on the DE2 boards. And you can do that. And you can get your own little drop-in ARM processor and drive the LEDs and all the different I/O devices, and it's cool. But having said that, if what you really wanted was to run a 16-bit ARM equivalent processor, it's much cheaper to just get an ARM processor. I mean, the DOEs are not that expensive. And if you wanted to do it upright, you'd get a Raspberry Pi 4. That's cheaper than a DE2 board. So, here's somebody who did an Arduino 6502 emulator. I actually bought one of these. I bought an Arduino that emulates an old Kim 1 computer. So here it is. Somebody's running BASIC, and they're counting to 25. But, so what? That's my thing, If the goal was to learn how to write BASIC for the Arduino and you thought that was educational, then great. But if your goal was to get real work done, I'm not convinced that's a good way to get it done. Here's somebody who got a little BASIC interpreter on an ESP32. I guess you can do any language you want if you're willing to put in the time and the effort. But I haven't seen anybody make a viable Java virtual machine for the Arduino. I don't think. So here's somebody who wants to run the JVM on the Arduino. And what's going to happen is he's going to make this question up and somebody's going to say, that's not an appropriate question for this forum. Why would you want to do that? You should never want to do that. And other sorts of, put downs. And, these guys are all going to get sort of the same response, I imagine, which is going to be, don't bother. Now here's, there is a Java interface to the Arduino using the serial port, and you can use the serial port or the Ethernet or whatever you like. That's not an unreasonable thing to do because you're on a desktop platform and you're communicating to the Arduino remotely. And so now you're using the Ethernet as a substrate. And that's a perfectly valid way to go because your Arduino is going to give you the robust interfaces to ADD converters and stepper motors and servos and sensors and all these other things that your Java program on the desktop computer might not have available to it. So if you wanted to measure something like how much current does my motor draw when it starts up, right? So then you get the Arduino measuring current until it exceeds a threshold, 100 milliwatts. And then all of a sudden you start sampling every 5 milliseconds during the startup of the motor. And then you could take that and log it out. And, you can log these things out to the network. So in this case, I have a little demo for you so that you can see it. It's a thing called Thingspeak, which allows you to take data and graph it in real time. So what you can do with Thingspeak is, and here's the example right here. You'll see what I've got is a load cell, and it's connected to Wi-Fi through a ESP32 or 8266, 8622. I think it was an 8266. So this is the ESP 8622. I thought it was an 8266. So I might have this backwards. And in any case, I've got the web server running on the little microcontroller. And when the voltage changes, you can see it updates, but it takes a little while. That's what Thingspeak will let you do. It'll let you push the data out as things change. So as an embedded system, it can log the data out to the network and even give you a graphic depiction. That's what Thingspeak is about anyways. So as soon as we do a call, you can see the update. Here's the update. So you can give it a second, and there it goes. There it updates. So that's cool. That'll give you a little value add when you have a networked embedded system. So you can do that with load cells. You can do it with anything you want to measure. Put it that way. Load cells are really nice because they give you a lot of dynamic range, like 18 bits or more, 24 bits in my case. But then sample rates are low, like 100 samples per second, things like this. So that's not particularly good. And then there's a question of configuration. So I tried to solve the configuration problem for Wi-Fi by creating a special access point in the microcontroller. So you go to the microcontroller and you tell it which of the Wi-Fi SSIDs to use, and then it prompts you for the password, because the controller itself has no graphic user interface other than the web interface that you supply. And so this is an argument to the command line. And here is the scale controller. You can go to the scale access point, and it gives you your own little Wi-Fi manager in the scale controller. And what you want to do when you configure Wi-Fi is you want it to go through a scan. So this is a scan of all of the SSIDs that it was able to find. I picked out Netgear, and I gave it some sort of wacky password and hit save so that it could rendezvous with the Netgear next time it gets rebooted. And so now it saves the credentials in a double EEPROM area. So during reboot, the credentials are retained. So that solves the configuration problem when you first plug the scale in. If it loses connectivity with the Wi-Fi router, then it'll turn into an access point again. Then you go straight to the access point, and then you go and do the configuration over again. So that's a way to handle the configuration problem for Wi-Fi on a device that has no LCD readout or buttons. So that's kind of a nice way to go, actually. And it gives you an opportunity to interface to a wide variety of different things and configure it. That's, a little bit beyond the scope of our course, but if you ever want to get into the Internet of Things, it's really nice to know that you can do stuff like that. Here's another one where I'm using Bluetooth as a communication protocol, and there's a chat program that you can use in Bluetooth. And what I did was this is a Arduino Pro Micro in here, and this is the Bluetooth module over on the right. And there's a microstrip array, microstrip antenna up on the top. This is called the HC05 Bluetooth module. This little black wire, that's going to be your ground. The transmit goes to the receive, and the receive goes to the transmit. And what you want to do when you do these kind of setups is you can use a program called Circuit.io. So I used Circuit.io to guide me through the setup on this one. So that you kind So here's where the power comes in and gets distributed to the HC05 and also to the Pro Micro.
So now you can see this is not exactly a Pro Micro, this is a regular micro. So you want this red to go to the VCC on the micro, or the VCC for
The wiring for the Pro Micro and the Micro are basically the same.
to go down to the ground, which is over on there on the Pro Micro, but ends up being
Also, when you use Circuit I/O like this, it gives you sample code.
the transmits and receives go to the transmit and receives over in here on the Pro Micro.
The sample code is totally useful because it'll let you bootstrap the hardware, and you get to know for sure that things are working.
Quick swap, pick another controller.
Now, here's the cool part.
I guess
You can swap in something like an Arduino Uno if you want to. So here's an Uno. Put the Uno in, click OK, and now it's an Uno, which is really cool. So if you say, oh, I don't have a micro, I only have an Uno, you can swap it in and it wires it for you. And here's the prototype code. And that you can cut and paste into the IDE and it'll just work.
But what I did was a little bit different. I went down to the IDE and created my own little test facility so I could have a chat program.
So for me to do a chat, I need two Arduinos with two monitors. One monitor is associated with the IDE, and the other one's associated with CoolTerm.
You don't need to do that, but I decided to use the same board, right, for transmission and reception.
And we're using 9600 baud to communicate.
Arduino monitor. This is the
So on the one side, if I hit enter, it'll come out on the right. And on the left, it seems to be responsive to one character at a time as I type.
Here, what we'll do is we'll write something like this.
So each time I type a character, it comes right out, which is kind of cool, actually. So now we got Bluetooth communication going.
To see how that's set up, go to the options on here.
You don't have to see how to set up a serial port because that's boring. Here's another example of something that I was playing around with. This is called the PS2 Keyboard. PS2 Keyboard has a special DIN connector. So this is a really ancient keyboard, like an IBM XT keyboard with an old style 5-pin DIN connect going to a new style PS2 interface directly to the Arduino Uno. And then the Arduino Uno reads in the serial clock and the serial data as you type the keyboard and echoes it out to the console. Once I got this working, I thought, man, this is so cool. I've got a keyboard interface to the Arduino. And I thought that's just slick. And the funny thing is the 5-pin DIN and the 6-pin DIN, PS2 interface, they are pin for pin almost identical, except for they have a pin 6 on the PS2, which is not even connected. So it really is a 5-pin interface with data and clock. And it's just like an I2C interface. And when I got this from China, I found that they had mislabeled all of the silkscreen pin assignments, and it really messed us up. But I got that squared away, and then wired everything properly. And once I did, things started working again. So that's a 328p based Arduino Uno, but this works the same as the leaderless chip carrier style Arduino. And here I am typing on the keyboard, and it's coming straight out on the console, which is, I think, pretty cool. We got this working also with using a so-called USB host shield and a USB keyboard. But what I haven't been able to do was to plug a USB keyboard into the PS2 converter and then plug that into the Arduino. That just didn't seem to work for whatever reason. So that's a that's a fundamental limitation, perhaps in my understanding of these sorts of things. So that's that PS2 keyboard. So I guess this truly is the interface everything to everything kind of thing. Here is a USB host shield. This will work with I don't know why it says that. It looks like an advertisement, but it shouldn't be. So here's a USB keyboard, and that's plugged into the USB host shield. And that needed a little extra wiring. You can see there's a little happy hands at home look with the yellow jumpers and the green jumpers off on the corner here. And so I had to solder in these pads. I had to solder in these header pins and then wire in those jumpers, and then things started working again. Now here's the Mega, and you can see the Mega has a totally different layout than the Uno. USB host shield was surprisingly expensive. That was like a $19 shield, which, you know, kind of led me down the path of, well, why do we need this? Why can't we just treat it like a PS2 keyboard with a converter? But that didn't work for whatever reason. Oh, and the mouse works too. So you can get the USB mouse. So if you wanted USB stuff for your keyboard, well, for your Arduino Uno, you could plug a keyboard or a mouse in. And it allows you to do a hot plug of the keyboard, and then you can plug in the mouse. So that's pretty slick. I like that. But I thought the USB host shield was too expensive. So if you're clicking on the right, you can see it's coming out. He's reading the button up, button down stuff. So the camera work on this leaves something to be desired. And I know the demo is not exactly riveting, but you can kind of get the idea. So this took a lot of work to do, believe it or not. That was not easy. So that's my those are the demos. You got to see the scale controller and Thingspeak. I got to show you the PS2 keyboard communication, the USB host shield, the Bluetooth. So that was cool. And now here's a real hacky kind of thing. This is creating a reverse shell on the Mac. And what that does is it allows you to use a so-called penetration test. So here we're using a bash script, and it's going to give us a command line interpreter that we can go into the computer in remotely with, and then we can do what we want. We can type whatever we like.
And then what we'll do is we'll start a bash script on the target machine and redirect into port 1234 on the command and control machine's IP address, which in my case is...
So 1234 is the port that I'm using. The local host is 127.0.0.1. And bash is giving us an interpreter, and it's going to give us a callback to the other machine. And you can see it's got a bash prompt. And now I can just type in bash commands, and that'll give me the ability to do whatever. Wreck mayhem. So that's cool if you can get somebody to invoke the bash script on the remote machine. That is, they have to type that stuff on the target machine. But to get that, well, we can use various kind of penetration systems. We have something called RF Leo, which lets us type in remotely. But there's also an RF Micro, and there's other ways to do it as well. So that's the penetration test. I consider that ethical hacking, because we're hacking our own machines to test to see that we can get in. So that's the ethical hacking. So any questions about the final? I think we kind of beat a dead horse with that final. So I just wanted to give you a few demos and wrap things up and ask if anybody had any last minute questions, you've got a final due next week. It's on the 17th. So you've got a whole week to deal with it. Please don't wait till the last minute. People were emailing me last night when I was ready to call it quits for the evening. Oh, can you zoom in? Can you do my debugging for me? Can you do this, that, and the other thing? And I was like, man, why can't you guys start a little earlier? And that's not, anybody in particular. I just think people should just manage their time a little better, but that's, that's that, and it's done. Any questions about the final project? That's all done now. So hope you guys did okay. I haven't looked at it yet, and I hadn't started grading. So that may take me some time. So if that's all, I think what we'll do is we'll end the class a little bit early today. Stay safe. Enjoy your break. And enjoy the rest of the day. It looks like a beautiful day out, and I've been spending the whole day inside.
Have a good break, Professor.
You too. Have a good
Professor. Have a good break.
Thank you. Thank you.